When discussing the differentiability of piecewise functions, as in example 12, you have to be very careful with how you look at these. So for the first part, it says to find the piecewise derivative function, one from the left of 1, one from the right of 1, using the formal limit definition of the derivative. So let's say first from the left side, we have f of x plus h minus f of x all over h, distributing that out. Okay, and you should see that the x squared's canceled, and you can factor in h out of the numerator. So it appears, scroll down just a little, okay, it appears that the limit is going to be 2. If we look at it from the right side, we're using a different function here. We have 2x plus 2h plus 1 minus 2x minus 1. It appears that quite a few things will cancel out here. We get 2h over h, which is 2. So, using the formal limit definition of the derivative, it appears that they have the same limit. Okay, let's see. And, and I just noticed, using the formal definition, I shouldn't have put this here. Okay, the formal definition has h approaching 0. Good thing you write in pencil, right? So then that would mean this is 2x and then 2. When you evaluate it at 1, then they're the same. Okay, so for part A, we are evaluating the limit as x approaches 1 from the left of f prime of x, which is our 2x. So that's 2 times 1, or 2. When we take the limit as x approaches 1 from the right of f prime of x, that is 2, because it's always 2. So based on our observations, it is f of x is differentiable at x equals 1. Now we're going to use the alternate form. I'll do that over here. The alternate form would be this setup: limit as x approaches 1 from the left. Remember, that one's f of x minus f of 1 over x minus 1. So f of x, we have x squared from this side, minus 1 over x minus 1. Good thing you know algebra, because you can factor this to x plus 1 times x minus 1. That will cancel out with the x minus 1 in the denominator. Plug in 1, we get 2. Alright, so now let's do the other side. The limit as x approaches 1 from the right. F of x this time is 2x plus 1 minus f of 1 is still going to be 1 over x minus 1. So on this side, we get 2x over x minus 1. If you evaluate that at 1, you're going to get does not exist, because you can't have a 0 in the denominator. Therefore, it appears that f of x is not differentiable at x equals 1. So what's going on here? The problem is that we didn't check. If we looked on the, I think it's on the last page, right, about continuity, maybe 2 pages back, continuity and differentiability, well, we never checked to see if it was continuous. All right, too far, okay. So if we first look to see if it was continuous, what's the limit as x approaches 1 from the left? You plug in 1 into x squared, you get 1. What's the limit as x approaches 1 from the right? 2 plus 1 is 3. So therefore, it is not continuous. And then that would imply that it's not differentiable at x equals 1. Okay, so if you're using piecewise functions, it's really important to check continuity before you check differentiability. So let's not make that same mistake when we do example 13. We're going to first check the continuity. All right. So we have the limit as x approaches 1 from the left. So that would be x squared. Plug in that, we get 1. What's the limit as x approaches 1 from the right? 2x minus 1. 2 minus 1 is 1. So f of x is continuous at x equals 1. That doesn't mean that it is differentiable. It means it has the potential to be. If we had found that this was not not continuous, then we could assume right away it's not differentiable. So let's check the differentiability. X approaching 1 from the left. That will give us x squared minus 1 over x minus 1. Factoring that, okay, just like we did in the last problem, we would get x plus 1 and 2. Okay, let's check it from the right now. 1 from the right. We're going to get 2x minus 1 minus 1 over x minus 1. That gives us the limit as x approaches 1 from the right of 2x minus 2. Still not quite there, but keep going. 2 times x minus 1 over x minus 1. Look at that. Now it cancels out and we get the same thing, the same answer as 2. So what we have seen there, that f of x is differentiable at x equals 1. All right, the next one you're going to have to do on your own calculator. Okay, there's another form worth mentioning. You can look at it. I'm not going to read it to you. Example 14, however, you're going to have to do it using your calculator. I don't have that. Depending on whether you have an 8384, an 89, or another type of calculator, you're going to get a different answer here. So I would like you to try to find, using f of x equals absolute value of x, find f prime of 0 using your calculator. All right. See if you could figure out what you want to do there, and put your result, what you get, in your whisk, and then based on your result from example 8, what can you say about your calculator? Okay, that's very important. Put it into your whisk. Have a wonderful day.